So today we're going to be looking at a two-sample mean significance test, and I found this online. So here's what we're working with. Here's the problem. They're trying to test whether a new low-fat diet helps obese people lose weight. 100 randomly assigned obese people are assigned to group 1 and put on a low-fat diet. Another 100 are put into group 2, and they have approximately the same amount of food, but not as low in fat. After 4 months, the mean weight loss was 9.31 pounds for group 1 and 7.4 for group 2. So I took that information and I've already written that down. So let's see what we've got here. Okay. So we'll kind of come back. I used my notation for group 1 and group 2 was low fat and not low fat diet. So I got the X bar, the S from the problem. And now I do need a difference. So because we're trying to compare these two groups to each other, so we're definitely going to be needing our X bar low fat. So I'm going to do larger minus X bar not low fat. And our difference is 1.91. Okay, now we're doing a significance test, so the problem didn't really specify, but they would say something like, is there sufficient evidence to say that eating low fat will help you lose more weight than not eating low fat? Let me just glance at the problem one more time. I want to see. Yeah, so that's the mean differences in the weight loss. Both of them had some sort of weight loss. Okay, so significance test, we have to have our HO and our HA. So HO is that the mu of the differences, there's nothing special going on. So if you subtract the differences of the low fat weight loss and the not low fat, the assumption is there's no difference. We've got nothing else to go off of, so we just assume nothing special is going on between these two groups. They will be the same. The alternative, though, is that eating low fat will help you lose weight. So we're going to make that greater than 0. And we have to, in words, make sure that the Greek letter gets defined. So mu of low fat is the population mean difference in weight loss? Mean weight loss. That's what we want. For low fat. And then mu of not, I should probably write that out, low fat, because this is where you can actually tell them what you're using for your to simplify this. And then this is the population mean weight loss for not low fat. Yeah, they don't know what LF is and NOT, so I'll make sure I put that there. Okay, so here we go. Let's do conditions for, again, remember significance test, you have to have your HO and your HA and define your Greek letters like you would do all the time. So, conditions for a two-sample mean T significance test. And if you're on a mean problem and you don't know the population standard deviation of mean weight loss differences, which we don't, we are going to be using a T distribution. And again, we're just going to use the calculator degrees of freedom. It used to be n-1 if it was just one sample, but so we're going to use calculator equals, we'll fill that in later, degrees of freedom. Okay, now number 1, you've probably done this more times than you really would have liked. is, now we start thinking, okay, is this a simple random sample? Well, guys, this is an experiment. So there was no sample. These 100 people, I don't know, I'm not going back to the problem, but maybe they were volunteers. We don't know how they were, where they came from. So what we're going to do is we're going to say the data come from two groups in a randomized experiment. The two groups can be viewed as independent. Okay? So, randomized experiment, the two groups are independent of each other because they've been randomly assigned to the different, to the two different groups. So, normally you would write independent simple random samples from the two populations, but now in order for them to be independent, we need to make sure that they've come from an experiment. That's our other option. Now, the second condition you would check, is the population greater than 10n, but you only do that when you're sampling without replacement. And we know we're not even sampling, so all you need to say is now here, the first condition talks about the two groups being separate from each other. The second one is going to talk about the individuals in each group. So knowing the weight loss of one person should not affect the weight loss of another. So that's like within the groups that these people are independent. So these two conditions we've got, therefore, independent, I guess obese people. Okay, and then I go to number 3. Third condition on a mean problem. So no pi's, no n times pi or n times p hat. I am going to, where's my little thing I had earlier? I probably put here. Here it is. So third conditions for mean. We need, I kind of go down the list. Oh, this is nice. N is greater than or equal to 30 for both of the groups. I was thinking about box plots when I first started doing this problem, but if you had to, in this situation, they didn't give you the data, they just gave you the average difference. So, if you'd almost have to, if you had to do box plots, because if N was really small, you'd actually have to say something, along the lines like assume the box plots of the samples are, have no skew and no outliers. But in this situation, CLT, less writing that I have to worry about. So we'll use that central limit theorem. We've got 2. So N of low fat is greater than or equal to 30. And N of not low fat is also greater than or equal to 30. So the central limit theorem will work. It'll say that both of these distributions will be approximately normal. So a T approximation is okay to proceed. So now, think about the differences, people, between what a confidence interval looks like and what a proportion looks like. If you have the Greek letter, you use it. We know the differences. Everything you do when you're doing two samples is about differences. So the Greek letter of the differences is going to be 0. That's going to go in the middle. So 0. Now your sample differences was the 1.91. So we're going to put that up here. And we are going to shade greater than, because we think low fat will lose more. They'll have a greater difference. Okay, so now your formula. From your lime sheet, my grape sheet. Statistic, English letters, minus Greek letters, divided by the standard deviation of the statistic. You're on a mean problem. That's the standard deviation of a mean statistics. We don't know sigma, you almost never do, so we're using the standard error when that's what we call it instead of standard deviation, and we substitute in S's for sigmas. Okay, so that's where everything's coming from. The difference, so we're going to take T is equal to the test statistic, which is what you're using, and we'll have X bar of low fat minus X bar of not low fat minus mu of low fat minus mu of not low fat divided by the standard deviation of S of low fat squared over N of low fat plus S of not squared over N of not. I'm just taking that from the line sheet. Okay, let's put the numbers in. The difference was 1.91 minus 0 divided by the square root of Okay, and now let's go to our calculator to do those calculations for us. Stat test, 2-sample test. It's not a proportion, it's a mean. 2-sample t-test. If you go into Z, by the way, notice they'll ask you for sigmas, which they never reported in the problem. So go back, get out of there. So this time I don't have L1, L2. I actually have just individual data, so I have to give it statistics. Please remember that the calculator is always going to do x1 minus x2. So make sure that that's what you want to enter first. So because I did low fat minus not low fat, I am going to enter the low fat first. But if you might have to change that. Let's say the not low fat was larger, that would go into my x1, s1. And then x bar 2 is 7.4 and 4.04. And then I had 100. And we are doing a greater than, so go ahead and just do that. I think I got all my data entered right. Okay, greater than, hit calculate. Don't pool. You only pool on a 2-sample proportion test. It won't even ask you about pooling. Hit calculate. T is 3.09 and your p-value is 0.001, and notice those degrees of freedom. Let's copy those into the title as well. 193.98. Woo! 193.98, and T is 3.09, and our p-value is 0.0011. Okay, let's write our conclusion. Plarring or pagaffering, since the p-value is less than, and we'll say alpha equals 0.05, we reject HO. There is sufficient evidence to conclude and I guess we can say the mean weight loss for a low-fat diet is greater than the mean weight loss for a non-low-fat diet. Okay, so P is less than alpha, reject HO. First sentence talks about rejecting or failing to reject HO. Second sentence, did you gather enough evidence? And we have a very, very rare sample that just occurred. So it's likely that the 0 that we assumed there was no difference is not the true difference because this is such a rare sample. So, okay guys, that's a 2-sample mean T significance test. We're getting close to being done with all this writing. Have a good day.